All right, so one quick announcement. Remember the computer science get together flippy dealy thing today is after class over in the inside the computer science suite. I think it's an S118, but I'm not positive where they're having it, but I encourage you to go to that. They do like trivia and crap, and there's good prizes. So I don't know what the best prize is, but a lot of times you get like an iPad, or I mean, it's not like bouncy balls. It's usually pretty decent prizes for the first couple. And they usually do one of those like icebreaker games where, find somebody who has the same size shoes as you, something, some stupid thing like that. And if you do really well in that one, that's usually who gets the first prizes. So show up early, compete to the death for that, and you can get your first choice for whatever the best thing is. Yeah, I know. Does anybody know, is that just in S118?
There's something about a meeting in the lounge, but I don't know how empty the lounge is at the moment.
Oh, well, there's furniture in there. Who knows? But go to that. I'll at least pop in. Let's see. So we did not have homework, right? We were doing our all right, we did our fractions. Oh, right. So right at the end of class, I started trying to do like a larger fraction. And I think if I remember, I like interject an error. So it would definitely scream at me somewhere. Yeah, finish this. All right. So let's actually, since we're doing this, let's actually just go ahead and expand this to get us where we want to go, rather than play I was trying right at the end of class to play the stupid math real quick to get me a numerator and the denominator that were roughly 2.1 billion or so. Actually, I guess we can just do that. So if we have F1 here, we'll just say that. So we'll have F1 is the fraction 2 billion over 2.05 billion. And here, we'll just get rid of all these things. I'll display F1 and I'll reduce F1. And then I'll display F1 again. So now we're not doing any adding or anything. We're just creating a giant fraction that still fits inside of integers and displaying it. That'll happen quick. Then we're going to call our reduced fraction function, which is going to, if you remember the way this works, is it looks at the numerator and denominator, decides which of those two values is smaller, right? And the smaller of those two values is they decides that's the biggest possible value that might evenly divide the numerator and the denominator. So it starts counting from there down to 1. So in this case, the smaller of these two numbers is the one that's just 2 billion rather than 2.05 billion, right? So we're going to count from 2 billion down to 1, looking for the first number that evenly divides both. Now, mathematically, the smallest number that could possibly divide them is the square root of the second number, but we're just doing it brute force to really drive this home. So really, we're going to have to probably go through, I don't know, close to 1 billion things before we even have a chance at finding a number that evenly divides both. Now, when you have a for loop that goes through 10 things, that happens really fast. 100 things happens really fast. 1,000 things still happens pretty fast. 100,000 things still feels instantaneous to us. But 1 billion things, you start feeling that. So I'm going to go ahead and run this. And we're going to see that it's going to show us our fraction. Oh, I got to remove my error, right? I'm not even using add fraction, so I don't have to worry about that right now. Give me a moment. I'm just going to break this for the moment. for no good reason. All right, so there is my 2 billion over that guy. Oh, I did. I reduced it pretty quick. I needed to pick a weirder value. But we're definitely noticing a delay, right? All right, so let's go way bigger. So we're gonna update this to our create fraction. We're gonna say this guy's gonna take in a long and a long for numerator and denominator. So now we can take plus or minus 2 to the 63rd power, which is what, like 9.5 quintillion or something like that. Way bigger than billion. All right, so, and then we're gonna have for our reduced fraction, we're going to change our fractions to be long arrays. So now it can hold larger values. So a fraction is going to be a long array. Create fraction is going to come in here. It's going to define a new array of type long, 2 buckets. It's going to put inside of the first bucket whatever numerator was passed in, the second bucket whatever the denominator was passed in. And then our display fraction will also take in a long again. We don't have to change the implementation of that at all. Just make sure it's capable of taking in a long instead of an int version of a fraction. All right, so now I can put some more values in here. And let's make sure reduce fraction. So here, just for the time being, I'm gonna take out these 2. Which one? 2 to the 63rd power is that guy. Here, we'll just make that 800. And we'll change that guy to that. All right, so let's look at where this guy is complaining. Oh, he wants me to actually label these as longs. Int to int. Too big of a value. I don't really want to do a long. Create fraction. Show you this point. What's up?
You have to change the int pointer to a long pointer.
Which one? Oh, this one. Thank you. Still thinks that value is too big. I do. Look at that. I'm testing you all over the place, and some of you are passing. All right, so this is going to take it along. This is going to take it along. Display is going to take in a long pointer. This is going to, I had to change it in a bunch of places, didn't I? Okay, we're not doing, well, we will be doing something with reduced fraction, so I'll make that a long. I fix it up there, long. This guy needs to be a long. So the smallest of the two values will be a long then. Technically, this needs to be a long, but smallest could be bigger than an int. We're good there. We haven't written add fraction yet. We can go ahead and turn that into a long. All right, we'll come back down to this. We want to do it here in a few minutes. It's a long, create fraction, long, long. Okay. New. All right. So we have giant fraction, display the fraction. Now we're going to reduce that fraction and display it again. Reduce fraction still taking it along. It's doing the same logic it did before. It's just is working on larger values. So now we'll hit run. And now it takes time. We'll let it run for like 20 seconds or something. You'll see it won't finish. And we're going to say, oh, that's a problem. Because now a program that we thought should run instantaneously, because the problems we were dealing with, the numbers we were dealing with before were trivial, little easy to count two numbers, right? But now we're working with a number that is a lot larger. You know, we also kind of saw that several years ago, if we would have done the previous example that took kind of what, maybe 2 seconds or something to run, that would have taken too long as well. Our computers are getting really good at doing floating point math multiplications, so it's hard to chase it. But right now we're working in the quintillion range, so we're pretty good. I don't think computers are quite here yet. All right, so we could sit here and run. I'm just guessing we could do the math and figure this out, but I bet you if we let this run, it maybe would not be done by the time we got back to class on Tuesday. It probably wouldn't be. I mean, my gut feeling is if we did the math on this, it probably maybe wouldn't finish for like 100 years or something like that. That's possible. I mean, I'm kind of just pulling numbers out of the sky, but the amount of numbers we're dealing with there, consider that you have a for loop that is counting down from 9.2 quintillion to 1. I mean, yeah, it's just a couple of digits on the screen. That's a lot of numbers, right? So we're going to say that's problematic. Well, so we could say, okay, well, we just aren't going to reduce fractions that are that big, and we'll move on with life. Unfortunately, fractions are kind of important, and we want to be able to reduce them. Remember in high school, I don't know whether your teacher said or not, how many of you had geometry in high school? Or geometry? Do you have a book that said Euclidean geometry on it? All right, so Euclid was a mathematician guy. And one of his inventions is he had this algorithm called the Euclidean algorithm. Did you talk about that in high school too? Euclidean algorithm? So the Euclidean algorithm solves a famous problem. You've seen GCD before? So this is greatest common divisor. Of two numbers. So really the idea of GCD is let's find the biggest number that evenly divides two different numbers, i.e. the biggest number that divides both the numerator and the denominator. So we need the greatest common divisor of two numbers. Well, right now we're doing, here's our version of greatest common divisor right here. Our version is, well, let's find the smallest of the two numbers. So we know we won't try, we'll only try the largest possible value, sort of. Then we'll count down from that to 1, checking every single number in between until we finally find the answer. This is a correct implementation of greatest common divisor, right? This will eventually, after 9.5 quintillion loops through, well, some subset of that, but potentially all of that, if they're prime numbers and they're only evenly divisible by themselves in 1, that'd be real fun if we had 2 gigantic prime numbers like that and forced it to go all the way through the entire loop just to get down and determine that, oh, they can only be divided by 1. That would take a long time. But, you know, this is a functional but crappy version of greatest common divisor. Yet this version of greatest common divisor probably would work fine in almost every real application, right? We're forcing it to try to have to work with these gigantic fractions. All right. But this Euclid guy, he had a famous algorithm called the Euclidean algorithm. I'm just going to grab that code right there, and we're going to just bring it into our project and implement it. Ooh. Oh, it's still running. It's still letting me know. Okay, so we could all agree we don't want to wait on this. All right, so we'll stop that. So what I'm going to do here is I'm going to do a reduce fraction 2, and this is going to take a long pointer of the fraction. And just right before this here, I'm just going to paste that in real quick just so we can operate off of that. I'm going to go up and make sure I prototype this guy, since I've already forgot we were coding in C++ once today. So I'll make sure I keep my prototypes going. All right. So we're just going to write a second version of reduced fraction, but instead of writing it the way we wrote it before, we're going to write it using the Euclidean algorithm. Now, when you look at this, that does not look like something that should be life-changing, right? It's kind of just a little a math trick. So we have a couple of variables. So we pass in 2 numbers. This could be the numerator. This could be the denominator. As long as that second number is not equal to 0, we set some third number, some temporary value equal to the current value of b. Update b to be whatever a mod b is. And then update a to be the other temporary value. Keep doing this over and over and over and over again until b finally becomes a 0. We're whittling it down. And then we return a, which is the greatest common divisor of those 2 numbers. All right. The math works. Okay, this is this guy's genius math solution to it. So what we'll go ahead and do is, just so we have our the numbers are line up to this algorithm, I'm going to go ahead and say long A is equal to the fraction at bucket 0. Long B is equal to the fraction at bucket 1. So now that creates our A and B here. All right, so I just extracted my couple of values from my fraction. And now I can just write that while loop. While B is not equal to 0, we're going to have a variable long T gets the current value of B. B is equal to A mod B. A is equal to T. And then keep going, and as soon as we return from this loop ends, we'll return the current value of A. So this guy takes in our fraction as a 2-element long array. I pull those pieces out into my 2 A and B's. And then this function here, while B not equal to 0, that's equivalent to this code right here. T equals B. B is equal to A mod B. And then A gets the value T. So this looks like the same algorithm. We've converted it to C++. All right, so we have that guy. So now what we're going to do, we've already seen that reduced fraction took a long time. on these giant numbers. So we're just going to use our secondary version of reduced fraction now. Reduced fraction 2. Oh, our version of reduced fraction reduces it in place. So I'm not actually returning my A. Instead, A is the number that evenly divides both of them. So I'll say the fraction at bucket 0 is equal to the fraction at bucket 0 divided by A. The fraction at bucket 1 is equal to the fraction at bucket 1 divided by A. And we have nothing to return. So A holds my greatest common divisor of both of them. So then I just go ahead and I reduce my fraction in place with those two values. We see we instantly got a result. Pretty much instantly. All right, so I like looking at that example because it shows us something relatively practical in that, you know, we don't view fractions as being, you know, overly difficult things, right? Doesn't seem like it should be something that should be pushing our computer to the limits these days. Yet we just saw an example without having to stretch too far and having to make some syntax error fixing, you know, which was obviously I did on purpose. But in general, we were able to pretty quickly create a solution with a program that probably was not going to finish in any sort of reasonable amount of time, even though it was functionally correct code. Now, what can be frustrating about problems like that is that let's assume that you, and for most of us, very first time I ran into this problem, I also didn't realize this was a real problem. That's why I teach it in class. I don't remember how old I was, but I used to do these online computer programming competitions. There was this site called Top Coder. And so you had qualified for these tournaments and stuff like that. So I was in this tournament, and the way Top Coder was actually fun. I really wish that they, I think they might still have it around in some place, but it's turned into some kind of recruiting thing for software engineers now. But you would have like the events. It was like an esport type thing, but it was programming, and there would be like an easier question, a middle tier question, or a hard question. You'd have an hour to answer all of them. And that you were in a room with other people, but then you'd have like 20 minutes before they ran your program through tests. You'd have like 20 minutes to look at one of the other competitors' programs to see if you could find a bug in it. If you found a bug, you got more points. You know, you got extra points, not just for your correct answers, but for proving their answer is incorrect before the system test proved it incorrect. You know, so we were doing this, and you know, this was like I don't remember if this was the easy question or the mid-tier question. Completely off my radar that this was anything other than just a trivial, let's just add some fractions together. I think it was the type thing where you had to add, have 100 randomly generated fractions where each number is between 1 and maybe 999,999, something like that. And you had to add all the fractions together and show the answer in a reduced format. Well, what it ultimately did is that by adding them together, it built up a fraction that got too big, so that reducing it became a problem, like we've just shown here. Not even close to where my mind was thinking at the time. Wasn't even considering that this was. I just powered through that program, you know, maybe wrote it in, I don't know, 5 minutes or something like that. Just like, okay, easy, points, go. We get to the end, and we runs it through the tests, and everybody else was in the same boat. Nobody thought about this as a time complexity problem. So nobody found a bug in anybody else's code for this one either. And so it goes and runs, and like we all failed the test. Because it was, you know, we passed like the first 3 tests, and all of a sudden, like, you know, ran out of time because like one of the rules was your code had to run in less than 10 seconds or something like that. But that was like something for every competition. So that didn't give us like extra information about this problem. It was just your code always had to run in under 10 seconds. So I'm like, well, why did I fail that? So I went and ran with one of their test cases myself, and it's like ran it, and after about a minute, still not done. So the first thing comes to mind when you see problems like this, you think, oh, is there an infinite loop somewhere? Because generally we want our programs to finish instantaneously. We expect our programs to finish nearly instantaneously. Even if there's a little tiny delay, a high percentage of the programs we write finish instantly. Well, this one did not. And so as a programmer, and frankly, I was not a beginning programmer at the time. I had been programming for years. So, learn from my mistakes, I guess. So I looked at this and I pretty quickly determined what the issue was, that it wasn't an infinite loop. But if you would put yourself in the shoes of a beginning programmer and you have a lot of code and it's taking too long to run, your initial inclination might be, oh, I have a loop that's not finishing. Where there's no stop case. It's just a loop that keeps running forever, because that's the only reason why this guy wouldn't be giving me an answer. And because there's only like 10 lines of code sitting in front of you here. And so that's what makes problems like this a little bit frustrating, is because your initial gut feeling is that, oh, I must just have a syntax error, an infinite loop. Maybe I have a semicolon like at the end of a loop or something. So the stuff inside the loop isn't actually happening, making the loop ever end. Something like that. So like in this example, if I say, well, B is not equal to 0, but I stop it right here, and the very first value of B is not 0, this is now an infinite loop. This will never finish because I have that little syntax error there. Because it's not doing all this stuff inside here that whittles B down to a smaller value. Does that make sense? So these are the kinds of debugging problems that can be the most frustrating, because you end up just making changes to your code over and over again, and you kind of lost track of where the problem originally was. So first thing you hopefully learn from this is, when you have a problem with your code, don't just randomly change stuff. Try to understand why it's a problem first. Backtrack it a little bit, because even though sometimes you could sit there and just change things 10 times in a row until you finally have tried every permutation and now it just works, if it wasn't based on at least an educated guess in the end, it's a problem. Because at that point you basically guessed your way to a correct answer, and sure, it works now, but you have no idea the zigs and zags that had to go into giving you that final result. Make some sense? So never write code that you don't at least have a rationale behind why you're writing it, even if it's just to perform an experiment. You might say, hey, I don't really know what this is going to give me, but let's just see what the value of this is when I do it. Maybe it's a different value than I expect it to be. So experiments are fine as long as you're asking a question and writing a couple of lines of code to prove the answer. But don't just randomly change stuff and just see what happens. That'll probably take you down a bad path. Okay. So that's a kind of a popular, actually, I would say not necessarily such a popular example of time complexity, but it's an example I like to use because most of us are not overly afraid of fractions, right? Yet we see that they can throw us a curveball pretty quickly. But it also is compatible with what I said when I first looked at the modulus operator, this guy right here. And this dude is important. Third grade math, remainders. We use remainder. Oh. Oh, there we go. I should have just taken it. All right. But that is actually related. So I won't go too far into this on this side, but if you remember last class, the beginning, I talked about the RSA algorithm. We were talking about the quantum computing stuff. This famous algorithm that all of our security on our credit cards and bank accounts and stuff like that is based on is 2 gigabit RSA, and RSA security is based on being able to find the prime factorization of a large number. And ultimately it is finding two numbers that would multiply together and get that number. Modulus is involved there as well. So it's something that seems so easy, the long division in third grade math that we just didn't like, yet we're still using it for like some of our most important stuff today. And where this guy is very unassuming, you don't really think much when you see a modulus operator, but some crazy stuff could be going on. All right, so I'll just say Euclid's algorithm, and you don't have to memorize that or anything. Just know that sometimes there are smart mathy people out there who have come up with cool little tricks like that that allow us to solve a problem that was a problem, but now with 5 lines of code is now not a problem because of their mathematical genius. All right. There won't always be a solution for every problem like that, but a lot of them have that. All right. A similar issue to that is detecting whether a number is prime. So prime numbers are numbers that are evenly divisible by just themselves in 1. So you might imagine if we're trying to ask, is a number prime? That's sort of kind of a very similar ninja move to what we were just doing when we were brute forcing, reducing the values, right? We would check all the values between the number itself and 1 and see if any of them evenly divide it. So a very similar type approach, right? Where we're having to check a zillion different numbers. So for prime numbers, we would literally check every one of those numbers because a prime number would not be true for any of those. Yet we're going to still check them. So as that number gets bigger and bigger and bigger and bigger, the number of values we have to check to disprove it being prime goes up. And for prime numbers, we have to check all those numbers. All right, so it becomes a very difficult thing. So there are some algorithms out there for determining whether a large number is probably prime. At one point I knew what kind of the error rate was there, but it's an estimator. So instead of actually going through and checking every single value in between, between 2 and the number -1, however that algorithm works, it gives you an estimate of whether this value is probably a prime number or not. And I mean, I'm pretty sure it's pretty accurate, but I don't think you can just take it to the bank. Like you might not want to, do space missions based on the result, but you probably could. But if you want a quick estimate, is this number probably a prime number for something? I think it gets the job done, and it's much, much quicker. All right. So we've been talking about data representation. And what I mean by that is we asked, how can, we're not typing out, how can we represent a fraction using the tools in front of us? All right, this is the way we solve any problem in real life. You got, you got something that goes wrong at the house, you need to fix it. You got to ask yourself, okay, well, what's wrong? What tools do I have available to me? And how can I best fix it with the tools I have available to me, right? Not all of us have expertise in everything. And then we also don't have all the tools that exist. All right, so, if you have 4 feet of snow that drops, and all you have is a wooden spoon in the kitchen, you're going to have a long day of shoveling. But you can do it because you have that wooden spoon. Or you just hunker down and wait till spring. Go into hibernation mode. All right. But we have to solve all the problems that we were presented with in terms of the tools we have available. So as we're solving these problems on here, I want you to continually think about what have we done so far in class. Because there is almost always going to be a better way of solving a lot of these problems. Right? But right now you're having to solve them in the context of what you know how to do. So when I said, hey, we need to represent fractions in our code somehow. Well, I told you how to do it the first time. And we said, so what's a fraction? Well, a fraction is a collection of 2 values, a numerator and a denominator, right? That's what a fraction effectively is. It's 2 pieces of information that I want to be able to pass around as a single thing. All right, so we decided to represent our fraction as a 2-element array. Not the end of the world, right? It was a reasonable enough approach. It worked. What's kind of the problem? If you were to point out weaknesses to our current implementation of fractions, what might you say? What's a weakness that we currently have? Not a functional weakness, but more of a, you know, I don't know, a practical use weakness, I guess. Where's our numerator in our fraction? Is that bucket 0? Where's our denominator? Bucket 1? You have to remember that, right? You have to remember that what we decided back when we wrote this is that we're going to go ahead and put the numerator at bucket 0. We're going to put the denominator at bucket 1. Kind of makes pretty good sense, but did anything actually keep us from putting the denominator at bucket 0 and the numerator at bucket 1? Other than we're, I don't know, not crazy or something, something like that. We certainly could have done it. Security through obscurity. I guess some people might also call it job security. If you write your code in a weird enough way that nobody else can fix it, it would be bad for them to fire you or something like that, is, I don't know, the old saying. So even though it worked, one challenge is we kind of have to remember where we put the numerator and the denominator. Well, what if we want something better? So put the numerator at bucket 0 and the denominator at bucket 1 in an int array and called it a day. This required us to remember where we put the various pieces. Now, not the end of the world in this case. You know, we're not keeping track of 700 different things and remembering that, okay, well, detail number 14 is actually at bucket 27 or something like that. You know, at some point it becomes more unruly, but initially, if you're just holding two numbers, bucket 0 and 1, really not the end of the world, right? But maybe there's a better way of doing it. All right. So what we're going to look at, we're going to say, how else could we do this? And I'm going to introduce the next two steps we're going through here. So we're going to look at structs. And then we're going to look at objects, writing our own objects. So that's where things are going to start getting fun. So right now, where we're at in coding at this exact moment is we're transitioning to, we're probably rolling through the, I don't know, early 70s or so, where the problems we were starting to solve with our computer programs started becoming more and more complex. And we started asking more of our language to allow us to represent these things. Because in the early days of programming, what we were asking our computers to do was fairly trivial, just math problems, basically automated things that people were already doing on calculators. But now we're asking a little bit more, a little bit more, a little bit more. So if we have some tools that allow us to better organize things, that would be cool. All right, so let's talk about structs. All right. So we'll start off real quick by letting some people immediately get a get their orientation here. How many of you have done stuff with Python? Dictionaries. All right. So a struct is a user-defined data type that allows a single type name to be associated with multiple values of potentially varying. It doesn't look spelled right, but is it spelled right? Varying? That's a weird word. I don't like it. This makes me feel uncomfortable. Values of potentially different types. That would have ruined my day. With multiple values of potentially different types. So if my data type allows a single type name to be associated with multiple types. that are also named. For example, we could have a struct fraction that holds a long numerator and a long denominator. And then we can create fractions setting the numerator and the denominator equal to values. All right, so let's look at this by example. So at the top of my code here, I'm going to go ahead, I'm going to create a struct. I'm going to call this guy a fraction. Oh. All right, and we're going to say a fraction is a long numerator and a long denominator. I've just invented a new type. So I have something now called a fraction that can hold two pieces of information. I happen to be holding both longs, but nothing keeps me from having 50 pieces of information in here. Some of them are ints and chars and longs and booleans and strings. Doesn't matter, right? It's a whole bunch of stuff. So I have a struct is a collection of name value pairs. Now, right off the bat, what's one advantage you see to a, well, let me just show you quickly a use here. So I can say struct fraction F1 is equal to, well, actually we would do this. Struct fraction F1 dot numerator is equal to 1. F1 dot denominator is equal to 2. So F1 would be the fraction 1/2 in my example here. And we'll update everything else with this, but so everybody's okay with this. This is another way, and this is another way of representing a fraction. Instead of a 2-bucket array of longs, this is a struct that holds 2 integers or 2 longs, a long numerator and a long denominator. Okay. What was the question I was going to ask? I almost started asking a question. I'm sure it was brilliant. Oh, it'll come back to me. Oh, yeah. So what's an advantage of using structs over arrays as you can see it right now? And it's not really exemplified in this example. Because this example, we're storing all the same kind of stuff. Go ahead.
Does it have to do with storage? Like only need if one of the fractor, then we were only needs to be like an int, the denominator needs to be a long.
Okay, well, so that is related. I'm not sure if that would make a ton of sense for working with fractions, but the punchline there is that with a struct, the types don't all have to be the same. So we could choose to have, in our example here, the numerator be an int and the denominator be a long, and that's fine. Whereas when we were working with arrays, at least based on how we know how to work with arrays right now, an array is a collection of same type values, right? So we basically had to hold a whole bunch of ints or a whole bunch of longs or a whole bunch of chars or a whole bunch of strings. We don't get to mix and match. We could sort of kind of mix and match based on what we know now. Anybody have a theory on how you could create an array that allows you to hold a whole bunch of different kinds of values in C++ using only what you know how to do today? It's a little bit of a hack, but it is using only what you've learned in class so far. Remember void pointers? When we called malloc and malloc, the memory allocate gives us a generic pointer initially. And then we typecasted it to an int pointer or a long pointer or whatever for working with it. Well, void pointers are memory addresses of undefined. So we could have an array of void pointers and inside of there hold a whole bunch of different, the addresses that point to a whole bunch of different kinds of values. It kind of makes sense. I'm not sure how useful that would be, especially in an older language like C++, where we would have to do some additional investigation once, because if I have this generic address and I tell you to go and check out, it's like you're a cop, go and check out this address and see what's going on. You get there, you start looking around, you want to find out what kind of value is this? Am I standing at an int, at a long, at a char? Well, they're all going to look like numbers to you, right? How long is this number going to be? Am I standing in the middle of the number? Am I in an array? So sometimes it might be difficult to determine what kind of thing you're actually standing in the middle of, whether it's a single 8-bit chunk of memory or it's a 256-bit chunk of memory for an array or something like that. But you could pull it off. You could store different kinds of values inside of an array using void pointers. Not something you're going to want to do, but we have better ways of doing it. All right, so right off the bat, we can say structures give us, or a struct gives us a more structured way of holding information. So let's update a couple of our things here. We're going to go ahead and say for create fraction, we're no longer going to create this a two bucket long array. Instead, create fraction is going to return a struct pointer, so a fraction pointer. So we're going to say struct fraction. That's my type. Struct fraction is the type. F, and then we'll say F dot numerator is equal to the numerator that was passed in. F dot denominator is equal to the denominator that was passed in. What are we going to return here? What value should I return there based on what I've written? Based on the return type, what type have I advertised I'm going to return? What have I said I'm planning on returning? What's a struct fraction pointer? What is that guy?
The address of both of them?
Address of both of them? Tell me more about that. What do you mean by both of them?
Since it's a structure, wouldn't it return both the numerator and denominator?
Well, the numerator and denominator are packaged together in the structure. You're right. But the struct fraction pointer is the address of the struct itself, which has those two elements living at that address. So we can kind of think of this as like an apartment with two roommates. They only have one address. The apartment has a single address, but there are two different elements, two different roommates at that address. So this guy we've advertised is going to return a struct fraction pointer, which is the memory address where a struct fraction lives. Make sense? All right. So what's the value that I would return right here then? I've built a struct here called F. I've set F's numerator equal to whatever numerator was passed in. I've set F's denominator equal to whatever denominator was passed in. So what am I going to return here if I've advertised that I'm going to return the address of a struct? I'll give you a hint. It's not the question mark that I currently have there. What is F? You had to tell me everything you know about F right there. What would you say? What kind of animal is F? Let me come up here real quick. You know what? We'll just It's gonna dump everything except for stuff we've written so far. Always rewrite it. Reduce fraction gone. Fraction gone. No, we're gonna have to rewrite that anyways. Okay. Let's make sure I have it. Create fraction. I'll just recopy it. Yep, it's good. All right, so I've written some stuff down here, but we're not going to use it just yet. So let me actually just comment it out for a moment. We'll just focus on main here. So I created a variable named f1 of type struct fraction. I said its numerator and denominator equal to 1 and 2, and then I'm going to output f1. So what we're interested in is what is f1? So it says no match. So cout doesn't know how to print out a fraction struct. It says, I don't know how to use an output stream to show you a fraction. That gives us enough information to tell us that what is f1? F1 is a fraction. What if I told it to print out the address of f1? Now we get an address. So f1 here is a thing. You can think of it like an int. F1 is like an int, or it's like a char. Okay, it's a physical structure that exists that happens to hold on to, in this case, 2 different values. So if you want to think of this like an apartment, it's got to be a big enough apartment for these 2 roommates to fit in it, right? And if they're longs, that means it's 64 bits. So that's 128 bits of data is stored inside of a struct, plus any maybe overhead that's taken for organizing the structs or something in memory. But when I build a struct here, it is a physical thing. If I pass this struct to a function, it gets passed as if it was an integer or a char. So it gets passed by value. So any changes I make to it are working on a copy, not the original. All right. So we saw right away here that cout did not know how to display f1. When was cout written? A long time ago? We didn't write it in here, right? Cout is something that the C++ people wrote. All right. When was fraction written? Before your very eyes in the last 15 minutes, right? All right. So we just invented this guy right here. Should we be surprised at all that cout didn't know about that dude? We're just giving him something we just invented. Said, look, you don't know how to print that? Come on. We literally just invented it. All right. But cout does know how to print memory addresses. So if I say, okay, here you can print out the address of f1. That's just a memory address. You can handle that, and it can. All right. So now down here in our create fraction, when I ask the question of what is f, f is a struct fraction. It is the actual struct, not the address of it. It is the thing. All right. Now, we've kind of talked about how we want to pass things around. So if using my analogy of our fraction kind of like being like an apartment, we're going to try to make it feel like it's a little bit bigger, even though fractions aren't huge, but it holds 2 values instead of 1. So we can kind of say this is starting to become a larger, more complex variable. So we're going to start saying that like something like a fraction, the struct is heavy. It's big. So realistically, in real life, we probably would not pass around big things by their value, right? You know, if somebody wants to borrow your car, you don't hand them your car. Even though your car is smaller than your house, you wouldn't hand them the car or the house. right? You would say, okay, here's my keys, or you can go find the car in front of my house at this address or something like that. It would tell them where to find your car, to borrow your car, right? All right. Yet, so this guy is an actual object. This is like the car in that example. Yet I've said that what I'm going to return is where you can find the car, the address where that guy lives. So I've created a fraction here. I've set that fraction equal to its values, but what I actually want to return is the address of that guy. And we're going to experiment with this a little bit. All right. So up here, we're going to call create fraction. On 1 and 2. So create fraction will come in here. 1 will be right here. 2 will be right here. It's going to create an actual fraction, set the 2 values, and then return the address of that fraction. Now, if we want to just see it, we're going to go ahead and print out the address of the fraction inside of create fraction. So we'll see what the address is here. Then we're going to return it. It'll return right here. We're capturing it inside of a variable named F1, and then we're going to print out F1. Why does it always do this? Fixes refresh, right? Anybody else getting it to run on yours? Okay, what's the outputs give you?
0 plus a couple lines.
Okay, so the second thing, the second element here, so down here you got a real memory address, right? It gave you a real memory address on this cout. Really funny why this is just not there we go. Got it. All right. So it gave me a real memory address on that cout, the first one. Okay, so this cout right here is this guy right here, which I then returned, right? It returned right here. That's what this guy boiled down to. I caught that address right here. And then I tried to print it out again. I got a 0. Why? This is review what we talked about last class. I keep reminding you how easy pointers are. They're frustratingly simple, right? When you get down to them, they're not that hard. But as soon as you start thinking about garbage collection and scoping and all these things, and you get too many other guys, you have too many chefs in the kitchen, right? Over there. Yeah, it's getting garbage collected. So this goes back down to our scope conversation from last class, where struct F here, that is a local variable of my of this create fraction. So that guy right there lives and dies with this fraction, with this function, create fraction. So as soon as this thing ends, this guy here, what I created, gets garbage collected. And when he gets garbage collected, that means that memory address no longer has things at it, which we are then seeing here when I print out and see, oh, we got a 0. That was a perfect waste of time. Trying to create a fraction that just got garbage collected as soon as it was done. All right, so what's our workaround? How do we fix this using what we And actually, I'm going to show something from somebody came up to me after class, last class, asking me about it. Somebody was passing in a value. Anybody, was that anybody who wants to take credit for that? That you were passing in a value and getting the response? You'll see what I mean by this. So I'm going to say, I'm going to show you why some old C functions look a certain way. I'm not necessarily saying I'm crazy about this way of doing it, but I'm going to change create fraction to return a void. But he's going to take a struct fraction f pointer, a struct fraction pointer as a parameter. Now I no longer will define my struct here, but instead I'll just fill my struct here. Is it you? Okay, yeah. All right, so I'll explain it here in a second after I finish it. But so I'm no longer going to define my fraction as a local variable here because I passed it in. But now I need to be able to set my numerator and denominator correctly. What is f? If I were to print out the value of f right here, what would print out? F is a struct fraction pointer. So if I print out anything that's a pointer, what prints out? Memory address. All right. So I'm printing out the value of a pointer. The value of a pointer will always, 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 always be a memory address. Doesn't matter what kind of pointer it is. Which means that right here, when I say f dot numerator, that's not going to work because f is a memory address. How do I access the fraction that lives at that memory address? That's my star f, the value at that address. Okay, this is nothing with structs. This is just how those syntaxes are applied. If I have a memory address and I want to work with the thing that lives at that address, I use the asterisk. Okay, so set the thing that lives at this address, and I think it's going to be okay with this. I don't have to put that in parentheses. Set that thing's numerator equal to this numerator. Set that thing's denominator equal to this denominator. I can print it out right here, giving me my memory address. I don't even need to return it anymore because I actually updated it in memory, right? So then out here, after I create my fraction, I can output F1. We'll still see it's the same thing. It's even kind of a waste of time to print that, but. Long int, oh, what did I? Long, blah, blah, blah. What did I do down here? Oh, I didn't pass it, my other thing. So now when I call create fraction, I'll pass it the two numbers, numerator and denominator, as well as the fraction I want it to fill in this example. Where is it reading from that? Oh, do I still have that? That's void. Oh, this guy's got to be void too. Okay, man. So now I got to introduce a new syntax. I don't really want to do that right now. So I'm just going to put this in parentheses. This will fix it. All right, so now it didn't complain about that anymore. It is interesting that it didn't print out I'm not getting a memory address here. Actually, let me show you this new syntax because we're going to be looking at it pretty soon here anyways. So right here, it was complaining that, oh, you are trying to call something numerator on a pointer. So what I could do is I can put this in parentheses and say, go ahead and resolve star f to its actual value, which is a fraction, and then call numerator on that fraction. Or I can use this fun syntax like that. So f followed by an arrow denominator. This guy and this guy do the same thing. So instead of using a dot and then the star thing here in parentheses, I can instead just say the thing followed by an arrow. So that's a pointer pointer. It's resolving the value and then calling the function at that value. So we would say that, yes, this is a new syntax, but doesn't this seem friendlier than this? A little bit less going on there, but there is some stuff happening under the hood that is still important. So well, so why don't I just leave that for right now? All right, so then I'm getting rid of that. All right, so based on this example, let me actually do this. Write this a little bit different. So I'll go ahead and C out F1 there, and inside here, I'll do a C out of F. Oh, I needed the address here. We already saw that it doesn't know how to print out fractions, print out addresses. All right, there. So we define our fraction here, real fraction, not an address or anything, real fraction. I call create fraction, I pass it the numerator and denominator as well as the address of the fraction whose scope is local to main. So this guy only disappears when main is over. So I pass the address of this guy into create fraction. Create fraction then used this guy, that address, to set the numerator equal to whatever is passed in and the denominator of whatever is passed in. He proved that he had the same address by printing it out, so that's why both of these are the same address. But ultimately, when all is said and done, if I say f1.numerator here, I'll get the 1. If I say f1.denominator here, I'll get the 2. All right, so create fraction took in 2 longs and the address of a fraction. It then filled in the values at that address. And that's it. It didn't have to return anything because it was operating off of the real thing in memory. So then when I came back here into main, I could just output my now filled up fractions information. And I only had to say f1.denominator here because f1 is just a fraction. He's not a fraction pointer. Make sense? All right. Now, you will see some old C libraries that work this way. That is to say that they will pass the value in like this. I would say it is not a common thing to do modernly. Modernly, we would have said we're going to return a fraction, a struct fraction pointer. Actually, I'll leave that there because I'm going to use it. So I'll pass in a struct fraction pointer into it. So or it's going to return that. So create fraction is going to just take in a numerator and denominator. Take this guy out. Take this guy out. And then what it will do is it will create the new fraction. All right, so we're going to see the same thing as last time. So just a few minutes ago, I said struct fraction f. And then I can say f dot numerator, f dot denominator, do things, but then we saw that this guy died off at the end of this guy, right? Saw it disappear. So what we can do is if we want to invent our own memory, what did we have to do? We had to say struct fraction pointer f is equal to struct fraction pointer malloc size of struct fraction. See, easy peasy. Very friendly, very friendly syntax. Good news is we're not going to be hanging around structs for that long, but we're going to move to objects pretty quickly. All right, but doing this should now allow us, so we now requested specific memory for our struct. We then, and this is a struct pointer, I then filled it up with the numerator and denominator, passed it in or got it out of our, so we're going to return f here. That's what this guy returned is our fraction pointer. Stored it inside of f1, print out the denominator. Oh, I still have it set as void. I have an extra dot. Chasing. All right, there we go. So I'll give you this as a starting point. So now you have an example of create fraction that takes in two numbers. Internally, it generates a global memory address for your fraction structure. So it doesn't disappear at the end since I allocated memory for this guy. So I get an actual fraction that doesn't disappear when this ends because I asked for the memory. I filled it up, I returned it. So now you have this new syntax with the little arrow thing. So what I'm going to have you do is I'm going to give you this as a starting point is rewrite the previous assignment, but using structs as the basis. I don't care if you use greatest common divisor or not. It would be cool if you did, but it's going to give you the same answer. We've already seen the exercise of working with gigantic numbers. This is more of let's work with structs and then we'll upgrade them to objects on Tuesday. All right. So based on what we just did here, I'll give you this code. Rewrite our implementation using 2-bucket arrays using structs instead. Make sense? All right. I'll see everybody on Tuesday. Don't forget about the CS get together across the hall. Big prizes, fun. So
I was talking to a friend about structs.